Okay, now let's start with part 4.1. We're introducing to you the idea of root mean square current, Irms, and average power P. So let's start first with the definition of root mean square current. So let's take this slowly. It's really a mouthful. The root mean square value of an alternating current or voltage is the equivalent value of the DC or direct current or voltage that will produce thermal energy at the same rate in a resistor. Okay, it's a mouthful, so I say again. The root mean square value of an AC is equivalent to the value of the DC that will produce thermal energy at the same rate in a resistor. Okay, I know this is a little bit confusing. We'll be unpacking it in the next parts for you. So let's imagine first and compare two sources or two currents. One is a DC source and one is an AC source. In the DC source, this is the power. The power of the DC is I DC square R. The power, the average power, right, in the AC will be I of the AC square taking average then R, which is the mean square current of the AC. Now, if these two were to be producing the same value in thermal energy, we can see that the IDC equals times R equals to the IAC square times R. Since R is the same, right? Same R, we can cancel it out. When we take the square root, we can see that the IDC, the current of the DC, is equals to the root mean square value of the AC, right? So here, in the previous part, we have learned the mean square value is a bracket on the outside and the square is on the inside. When you take the root of that, you call it the root mean square value, right? Or you write here IRMS, where RMS refers to root mean square. In your exams, you can always just write IRMS. We know what it means. Okay, so there's no need to spell it out in full. Okay, so a digital ammeter that's set to AC mode, right? This is for those who are interested, right? It reads the IRMS, right? So in our practicals, in the A levels, we generally don't use AC because of the dangers that it can come with, right? Next, this one is something that we need to explain because this is common. This used to be common knowledge. If you are, or rather, if you are someone who is very handy, who does a lot of electrical repairs within the house, you will know this. That they have ratings on them. But you need to know that the rating, when it says here 240 volts, it's not 240 volts peak value, right? It's a 240 volts RMS value, right? And the 100 watts here means that's the average power of the light bulb. So this is something that you need to know because it comes out in different questions. Yeah. Next, right? By using RMS, why do you need to do RMS values, right? So one of the questions that I get often is, why do you need to complicate matters? Can't we just use the mean square current? Well, because you want to calculate power, if you keep using mean square values, then you need to keep square rooting it, right? So the idea here is to just introduce something of the same units as a DC current, and we call it RMS values. And therefore, right, we can use the equations that we have learned in DC, right, DC circuits and COE, and apply them in our AC circuits too, right, which makes our life a lot easier. Okay, so with reference to the previous section, we learned that power is given by mean square current times R, right? But it can then rewritten as, after what I have taught you today, in this just previous slide, that it could be the IRMS current, root mean square current squared times R. Okay, where root mean square current is given by this symbol, It's called the root mean square current. And I want you to now see very clearly, right? Oh wait, let me finish this first. So in the previous slide, I said that you can use the equations that you learned from COE, right? And apply them to the root mean square currents. That's what I meant. Right? You realize that the average power is also given by the root mean square voltage multiplied by the root mean square current. And it's also given by the root mean square voltage square divided by current. So all these equations are very similar, in fact exactly the same as what you have learned in current of electricity COE, and just that we apply them in the root mean square in the AC topic, right? So back to what I was saying, right? Here I need to explain a little bit about this root mean square current, right? When you say it out in English, the name is root mean square, but right, so that's what you say, root mean square current. But mathematically, right, you actually do it the other way around. You actually take the current, you square it, then you mean it, then you root it. Okay, so this is something that you need to be aware of, right? The mathematical sequence is actually the opposite of how you name the object. So one more time, you take the current, you square it first, then you mean it, then you root it, and that's actually the root mean square current. Okay, so let's look at an example. If you recall, the first experience that you actually have with root mean square is actually the root mean square velocity. Actually, what I'm teaching you here technically is not new because you have learned about it in thermodynamics, right, or in temperature, right? So if you look at this, what is the root mean square speed of these molecules? So the first step is to list out the speeds first, right? So if you take rightwards as positive, the speeds here are minus 500, 300, 100, 100, 300, 500, okay? You square them, right? Remember the first step of a root mean square is to square. So you square all of them and take the mean. So what's the mean value? There are 6 particles here. So if you add 500 square, there's 2 of them, so there's 2 of 500. There's 2 of 300 square, and there's 2 of 100 square. So you take the sum divided by the number of particles. That's the mean. Okay. So you square it, you take the mean, which is the average, then you take the root, and you will get the following answer of 342 meters per second. Okay. So this velocity is the root mean square velocity. Okay. And with that, we come to the end of part 4.1.